In this lecture, we will be learning the Knight-Bayes classifier. First, we'll take a look at the Bayes rule. Bayes rule gives a way of swapping probabilities. So the probability of a hypothesis given evidence can be written as the probability of evidence given hypothesis multiplied by the probability of the hypothesis and divided by the probability of evidence. So we say individual probabilities such as PE as the marginal probability of the evidence E, and PH is also a marginal probability, but it has a special name called the prior probability of the hypothesis. This is because even before observing any evidence, we have this much of probability that the hypothesis will occur. And PE given H is called the likelihood, and how likely that we are getting this evidence from this hypothesis. And PHE is called posterior probability of the hypothesis. So here the posterior means that we have already observed the evidence E, and after doing so, how much are we confident about this hypothesis being true. So take an example here. Let's assume that meningitis causes a stiff neck, 0.5 probability, and meningitis occurs once in 50,000, and stiff neck occurs slightly more frequently, 1 in 20. And we are required to compute the probability of the meningitis given that the patient has a stiff neck. So here the hypothesis is meningitis, and our evidence is that this patient is having a stiff neck. So we have PH, PE and PE given H, and we can use the Bayes rule to compute the probability of H given E, which is 0.0002, which is quite a small number. So from this analysis we know that the chances of having meningitis just because having a stiff neck is quite small. To get an intuition about how this Bayes rule is derived, we can consider this hypothesis, which is shown here in a blue color circle, which is covered by two types of evidences, E1 and E2. And because of this, we can write this hypothesis coming up of several factors. So we have the evidence is occurring, E1 occurring, and when E1 occurs, what is the probability of observing the hypothesis H being true, plus evidence 2 is true, and given that how much we are confident about the hypothesis being true, and so on and so forth. So the Bayes rule can be easily derived by using the definition of conditional probability. So we have PH given E and we have PE given H, and if we divide one equation from the other, we get the Bayes rule. So in many cases we are not actually required to get the final probability, and we can make decisions just by looking at the proportional scores. So this form is called the proportional form of the Bayes rule, where if you are given some evidence, so we know this evidence is true, it's already given to us, and we are considering several alternative hypotheses, and we are required to select the most likely one out of those given set of hypotheses. So we don't actually need to compute the probability of the hypothesis given evidence. We can fix the evidence, we can drop that factor and consider the relative sizes of PE given H multiplied by PH. So it's good to remember this, at least this form of the Bayes rule, which is posterior is proportional to the likelihood times the prior. And the naive Bayes assumption is called naive because it is assuming the evidences to be independent. So according to this assumption, if we write the hypothesis H as condition upon multiple evidences, in here we have n number of evidences, then we can use the Bayes rule to swap these probabilities. And if these evidences are mutually exclusive, then the joint probability of those events can be written as the product of individual probabilities. So for two independent events A and B, the probability of both these events happening at the same time, which is called the joint probability of A and B, which is shown in PAB, equals to A given B and probability of B. And if, for example, the two events A and B are independent, then A given B is independent of whether B occurs or not and will be equal to A. Now if you substitute this back in our formula, P A given B, then we have P A probability of joint probability of A and B becomes the product of probabilities P A and P B. So having this naive assumption is actually independence assumption is making life quite easy, because we don't have to observe the joint events any longer. We can just observe the individual events, and from there we can infer or compute the probability for the joint event. So assume that we are considering this hypothesis that engine does not start, and we have evidence for this, two evidences in fact, whether the battery is weak or we don't have gas. And if we did not assume these evidences to be independent, then we have to observe situations where both A and B happens, and how many number of times out of those situations where H was true versus H was false. So the number of cars that we can find where both A and B are either true or false might be much more smaller compared to the cars that we can find where either one of the two events are true. So again we'll do this table that we used in the decision tree learning, where we wanted to predict whether a particular match will be played. So it has two outcomes, it can be yes or no, and we have four attributes: outlook, temperature, humidity and windy, to predict this variable play. So given a test instance X where we told that outlook was sunny, the temperature was cool, the humidity was high and it was windy, we want to compute the probability of play will be yes given this test instance. So we want to compute play equals yes given the test instance X, and this can be swapped by using the Bayes rule as X given play equals is multiplied by play equals yes. So the first term, the likelihood term, can be written as the product over individual attributes, and this is shown in the next line, and we can compute these conditional probabilities using the fractional counts from the previous table. So for example, if you wanted to compute this outlook equals sunny given play equals yes, we'll first need to find out the situations where play was yes. So we have 9 such cases, and out of those cases we have outlook equals sunny in 2 cases. So we are getting this 2/9 factor from there. So you can similarly compute the other probabilities and you will get this value 0.00529. We can do the same computation for the other outcome of the hypothesis, which is play equals no, and you will get the value 0.0020, so which is smaller than the previous case, so we would predict that the play will be yes. Note that however the two scores do not add up to 1. So that is because we considered only the proportional values, and if we actually want to compute the probabilities, we can use the fact that the summation of the two should be equal to 1, and we can divide by the summation in order to convert these proportional values to probabilities. So we see in this case the play equals yes given x will be quite high with the 0.72 probability. So although this is quite a useful classification algorithm, sometimes this independence assumption is too naive. So it will be too naive to assume that, for example, the probability of the Liverpool football team winning a match is somehow the sum of each individual player scoring a goal. So we know that football is a team sport, so you will have more than one people involved in a particular goal. So these type of things are not taken into account by the naive Bayes classifier, but this independence assumption arises in various types of classifiers. For example, linear classifiers such as perceptron would consider the contribution from individual features to be independent. So you multiply each feature by its weight and then you take the sum of those products. So the sum or the product it doesn't actually quite relevant, because if you take the logarithm of the joint conditional, and if the two events are independent, then they can be expanded as the sum of the logs. So depending on whether you are talking about the log probabilities or the probabilities themselves, you have either the summation version or the product version, or arising from the same independence assumption. The real problem with using naive Bayes is that sometimes you might have some factor, some probability which is 0. That's because we didn't observe that event in our training data. So irrespective of all the other terms, they might be quite high, but then if you just multiply by 1 0, so you get the total posterior to be 0. So this is quite common in text classification situations, because we might not actually observe a particular feature in a particular class in our training data. That is because, not just because that feature is not relevant when predicting that particular class, that could be because our training data set was too small. So if we had used a larger training data set, then it could be the case that we could observe this particular feature and it resulted in a non-zero conditional probability. So one way to avoid getting zeros is through what is called Laplace smoothing. So we can't actually assign probabilities to zero events without actually generating new probability scores. So if we are going to assign probability scores to these zero events, then we have to borrow those scores from some other place. So the way of doing this is called smoothing, and there are various types of smoothing methods. So we are discussing one simple method in this lecture, which is called the Laplace smoothing. It's also called the additive smoothing, because we would add +1 for all counts, to all counts, and then we need to divide by the number of features, the vocabulary size, which is shown by v set v's cardinality here, and that way we make sure that the total total probability will be always equal to 1. So to take this an example, to give this give an example of Laplace smoothing. So let's assume that we observed cat 9 times, dog 0 times, and rabbit once. So if we compute probabilities, that will be 9 plus 0 plus 1, which is 10. So the probability of cat will be 9 over 10. The probability of dog will be 0 over 10, which is 0. And the probability of rabbit will be 1 over 10, which is 0.1. So now let's smooth these probabilities using the Laplace smoothing method. So we'll add 1 to each of these values. So cat will become 10, dog will become 1, and rabbit will become 2. So we had 3 words. We added additional 3 plus 3. So we need to divide by not 9 plus 0 plus 1. We have to also add another 3. So that will be divided by 13. So the probability of cat now will be 10 divided by 13. The probability of dog will be 1 divided by 13. And the probability of rabbit will be 1 divided by 13. So that's Laplace smoothing for you. So we can use naive-Bayes classifier to do text classification. For example, if you want to do sentiment classification, we can use the naive-Bayes classifier. So we'll represent each review or sentence by this frequency vector. So naive-Bayes classifier assumes that all features to be independent. So this goes on to say that even if you observe the same word multiple times in the review, you should consider all these occurrences to be independent events. So the probability of the document will be the product of individual features probabilities. And if a particular feature appears multiple times, such as this burger appearing twice, you will have a square in the corresponding term. So here we have a square for the probability of the word burger. So we see that we have these multiple times probabilities occurring in the same document, which leads to what is called a multinomial Bayes classifier. We'll soon see what is meant by multinomial in this context, which is assuming two things. So the probability of a word occurring in a document is independent of its location. So it doesn't matter whether this word appeared in the title of the document or the body of the document, or maybe in a header or footer of the document. They will be all considered equally. And the length of a document is also ignored, which can be problematic at times, because certain documents might contain a lot of words, whereas certain documents might contain only a few words. So the documents that contain a lot of words will have a lot of probability terms multiplied together, which can in turn be actually quite a smaller number, because you're multiplying values, probability values are always less than or equal to 1. So we are multiplying a lot of values that are smaller than 1, so you could end up actually getting a very small number. So let's set aside these complications and assume that these assumptions to be true. I mean, it's okay to assume these things in practice. For example, if your documents are all of equal length, such as Amazon product reviews, then it's safe to assume that document length is irrelevant for the prediction of the class. So before we explain the multinomial distribution, it's worthwhile to take a look at the simpler binomial version. So if you consider this event where you flip a coin for n number of times, and you got k number of heads, so the remainder n minus k should be tails. So you want to find the probability of this happening. So we have k number of heads, which gives us p to the power k, and the probability of observing head was p. So the probability of observing tail should be 1 minus b, and we have a number of k times of those terms. And the factorial terms that are appearing in front of these two products is the combinatorials, that the number of times that you can get k number of heads by flipping a coin in number of times. So the multinomial distribution is the multinomial version of the previous binomial case. So where you, for example, if you flip dice instead of a coin which has 6 outcomes, then you have 6 different probabilities, and then you need to consider the number of different combinations of those 6. So that's provided by the multinomial distribution. And getting back to our text classification situation, so we have a representation of a document as a multinomial where different words will appear in the document and certain words might have multiple occurrences. So the total occurrences will be n factorial, and for each word we have its probability in a particular class and how many number of times that word was observed in that document, which is given by HWD. And this gives us the probability of observing a particular document in a particular class. So let's take an example. Again, assume that we want to classify this: the burger I ate was an awesome burger sentence, and assume that we did some stop word removal and we removed words like the, was, and that normally do not convey much information. So we are left with the other words, and again assume that we counted the occurrences of each of those remaining words in some positive and negative sentiment reviews. So we observe the word burger 3 times in positive reviews. So we have a burger 3 in the +1 set, and so on and so forth. And we can again compute the class conditional probabilities. So as the probability of seeing the burger in the positive class, so we have 3 plus 3 plus 4, 6, that is 10 reviews, positive reviews, and out of those 10, in 3 we observe the word burger. So the W given positive class would be 3 over 10. So we can use these values to compute the probabilities of the document becoming positive, coming from the positive class versus the document belonging to the negative class. And you can further assume that the two classes are equally probable. So beforehand, I mean, it has equal chance a document being positive or negative. So we set the price to be 0.5. And in technical terms, this is called a non-informative prior, which means the price not giving any information about the event that is going to happen, as in this case. So you can compare this document and it will turn out to be a positive document.